Hello everyone. So in this video we are going to do the asymptotical analysis of insertion sort. And I've already written some stuff here in order to save us some time. And what have I written? I've written the exact same code of the last video about insertion sort, about the correction proof of insertion sort. And do you remember that in that same video we had left proving this while loop correction as an exercise to the viewer? Well, it happens that it was wrong because I only had written greater than, strictly greater than, and what I wanted to have written was greater than or equal. Otherwise, this was wrong. So our correction proof was perfect because we have assumed that this internal loop from 4 to 6 was correct, but it wasn't. So if we had implemented this pseudocode, it would not behave as we were expecting, because we had assumed the correction of something that wasn't correct. So there's that. And while rewriting the algorithm down for us to do the asymptotical analysis, I've noticed that that loop was wrong, so it's now fixed. Another change I've done was, instead of using this page here, by the way, let me just check something. So this page here, okay, this page here, I also changed the for loop line for the while line because it's often easier to reason about while loops over for loops. So only because of that I've changed it for an assignment here and a while here, and this is an equivalent structure because we have been using a version of Corman's pseudocode, and Corman says that after the loop is finished running, the iterator is available with the last increment after the loop. And that's exactly what happens here, because we assign outside the loop, so it is in the same scope, and we had it here, it fails, and after the loop it is with the expected, with the number that would be expectable in Corman pseudocode with a Corman for loop. So that's just a note, it's good to have this equivalence, and that's what we are using. So that being said, we have to do the counting of steps. We are measuring time in steps, and we are using the RAM model. So we have seen in the previous video about the RAM model that when assignment is one step, and so this is a comparison. So it is oh yeah, I have forgotten about something here. Well, no, this wasn't intended. There's a missing 2 here. And also there is that same 2 here. Okay. So we will have to fix some things down here, but we'll get there. So this line runs n-1 times in the worst case and in the best case. So the best case, we have talked about that, was when the array was in order. And we are always assuming an array with more than one, with at least one position, or that is not an empty array. And yeah. of size n, and the n can be something, anything. So that's the definition we came up with. We have an unknown array with an unknown size that we know at least to be greater than 1 or equal, and that's the information we have about our input. And if it is completely sorted, that's the best scenario. If it is not sorted, the worst scenario is that it is reverse sorted of what we are expecting to have it in the end. So that, and that said, we run this always n minus 1, and while j is greater or equal to 0, we have two comparisons here, and we are going to run this comparison for each iteration of this while loop, the outer loop. We are going to run this comparison, and then inside this loop we also run it a certain number of times. Now, how do we know how many times we are going to run it? Well, we know that in the worst case it will always pass this condition. So, and then it will do this once because it has to correct only once. So we know that in the first iteration it is of this outer loop, it is going to run twice. In the second iteration, this line, this comparison, is going to run 4 times. And we do this over and over until we reach n minus 1. No, until we reach n times. 3, then 4, all the way up to n times. Exactly, because we have to compare each. We have the j, and we are assuming it is completely not sorted. So we will do this 2, 3, 4 until n. Well, how do we get to n to the summation of steps we are doing? And that's a really neat question. So we have this sequence: 2 plus 3 plus 4 plus n. And to get the exact value we are expecting, it's complicated. It can be really easy. It is easy to be confused about this. But we are talking about a simple mathematical, a well-known mathematical question. And you may already recall that this is an arithmetic progression, and you know how to compute the terms, and you maybe even know by heart what the formula is, and it's not a complicated formula. You see, if we have, it is known as the triangular number, because we usually have 1, 2, 3, 4, and what we are doing is we have 1, we have 2, we have 3, we have 4. So we are doing triangles, right? So it's a triangular number. There's another number that is the oblong number, in which the base is 1 more than the height. What's that? What am I saying? It's a rectangle, and for example, for 4, for example, you will have one ball, 2, 2, Maybe I will, it would, no, yeah. Okay, 2, 3, 4. And remember that rule of not drawing the square first? Yeah, it's the problem. Actually, let me even do something else first. My computer is dying. Okay. So let's do already this trace here. And we want 1 ball here, 2 balls, 3 balls. Oh my. Oh man. This is lagging so badly. 5 balls. And I think I'm going to draw the other ones, because when I use this tool the computer isn't keeping up. Okay. 1, 2, 3, 4, 5. And as I said, in this kind of number, we said that the base is 1 more than the 8, and that the 8 here is 4, and the base is 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what do I want to show you here? You see, if you add this up, you are going to end up with 10. And 10 is exactly half of this oblong number. So essentially what we are saying is that if we want the number of balls, or in this case the sum of this, then what we have is n, which is this times n plus 1, which is the successor of n, 5. And we are saying that n is our n, right? We said n was going to be 4, so yeah. And we divide this by 2, because we want exactly half of it. And that's how you get, it's a way of getting to this formula. Now the thing is, and you probably noticed, I have that formula here and I'm subtracting 1. That's because we do not start with the 1 in the worst case scenario. So we take that off. And you also have noticed probably that I'm multiplying by 2. That's because we have 2 comparisons in this line. And I had forgotten that actually, so I've now added that aspect. Alright, now you note that I'm subtracting 2 in the 2 lines below. That's because in these lines we actually are inside the loop, so we are not going to do the condition in which it will fail, the loop will fail. Right. There may be enough by 1, maybe not, but as you will see, it is not very relevant in this matter. I tried to avoid it. I tried to make this a rigorous demonstration of how to compute the asymptotic complexity of this algorithm. But there may be enough by 1 in some cases. I think not. Anyway, yeah, I think not. In the worst case, and you see, this is all trivial, okay? But let me now change the color of the pen to correct some mistakes. and the mistake is these two. So this 2 has to be multiplied okay, now it's all wrong. Yeah, but I think, God, this may be wrong because I'm going to edit it. So I'll actually do it in another color. The red will indicate that I did something wrong, and hopefully I will fix it correctly. So instead of having this equal sign here, we would have -3, I think. Wait, why -3? Sorry. Okay, it's quite different with that. It's not hard to do that 2 thingy, but for the purpose of the video, you may compute it with the 2 in your notes, but I don't think I'm going to do it here. I will have to erase it and just redo. I mean, if I propagate, again, I'll do it in red. If I propagate this, we would have one more of these structures, so instead of 3 it would be 4, and we would have -2. Then we would have yeah, so here in this step I only simplify some things, and I have so exactly, so this would be -7, but with +1 it would be -6, and this 3 we had eliminated it by adding this structure, but now this structure is gone definitely, and we have 2n squared here +2. 2n, yeah. Okay, and after that this structure again is gone, and what we have is n squared, which is this one, so 2n squared plus 6n, it's no longer 6n, is 8n, right? Because 4, 5, 6, 7, where comes the 8? 5, 6, yeah, we only added 1, so 7n. And this -6, it was -4, 4, yeah, 6, 4, we had 3, right? 4, we have 4. Wow, it's this 4 here. Okay, so 6, now it is 10, and here it stays 10, and 2n squared, 7n, and it was only simplification of this structure, but it no longer exists. So I think I actually did the correction correctly, so it's fixed, and we can replace the red thingies by actual actual something. So let me pick my color again, my writing color for this, and so instead of 3 it's 4. There it's -2 equal. Exactly. Have I done any simplification when I was copying it down? I did some simplification, yeah. Kinda could put already the minus. Never mind, let it go. So here and for n, yeah. So here we have 2. Where have I just erased the 2? Okay, 2 there and 2 there. And this term is gone, and we have -6 here. Oh my, it's lagging so much. -6 equal. And now we have equals to 2. And 6 becomes 7. And this term is gone, and it's -10. Okay, hopefully it's all correct. And now you see, we want to show that it is in big O of n, right? Of n, no, of n squared. Of n squared. So for that matter, we have to pick this expression we got here, and that's 2n squared plus 7. Actually, I'm going to leave this one down here, and I'm going to write it correctly above it. So t of n belongs to big O of n squared is the same as saying that n squared plus, 2n squared plus 7n minus 10 is smaller or equal to k n squared for every n greater or equal to n0, right? And we say let n0 be equal to n1, then we can say that n squared plus 6n squared no, once again we have to use what is there, so 2n squared plus, and now you can bump them up all, and we have done this in the previous 2 videos ago at least, that it's better to say, in the video about functions growth, where we solved a series of exercises. So 2n squared plus 6. Hi guys, I'm looking down and I'm doing again. 7n squared, and this is a minus 10, so we can just remove the subtracting term. We want the maximum order of magnitude, because with this we can say that this is equals to 9n squared, right? And so k is equals to 9. And note that despite we have done all this mess and all these changes, we actually ended with the same constant. That's interesting, at least. So yeah, we can now erase the wrong part. There we go. And let's study the best case scenario. And in the best case we also have this times 2, but it's a quick fix, this one. Let's move it up a bit. And I've actually forgotten to do something I intended before, that was moving this one a bit to the right. Where is it? Yes, it is. And draw a small arrow to the left of it. Exactly. So the best case is that we have this times 2. So that's 6, actually 7. Wait, no. 11. 11n plus 4. Not 4 either. It's easier to just do. We run it. Oh, sorry. No, sorry. On this one it's easier actually to add them back again. Otherwise I was going to do a stupid math error, because it was already simplified on the first step. So we look at it and we have 1 plus n, right, plus 1, 2, 3, 4, 5, 6. 6 times n minus 1. Alright? And then it's 0. So it's not really relevant. Now this is simplifying a bit. Oh man, it blocked it. Simplifying a bit, it is going to be 7n plus, minus 5. Come on. Oh, Christ. Okay, so 5, and then we now have this 7, 5, and it's negative 5. It was wrong here. So again, you bump them. And you have 7n minus 5. Now that, since it is seven n minus 5, and again you need to find a constant for each which it will be always smaller, because we are talking about wait, do I have the sign right here? Here the sign is everything in this one was wrong. Awesome. It will always be smaller on the right side, so you can just say, hey, then 7n then k is equals to 7, essentially. You can jump to the conclusion here. Then k is equals to 7. And that's how you do it, in a really simple manner. This is correct. You do all the steps, and it's a simple demonstration of the complexity of insertion sort. And I think that's what I wanted to show you in this video. And see you in the next one.